Hi, welcome to this tutorial on multi-objective optimizations, in which you will learn how to make improved decisions using a tool called Pareto Fronts, which I'm displaying right over here. Data-driven decisions is becoming more common within industries these days, but there arises an interesting question of the challenge of optimizing for multiple parameters. Most of the time, this is a non-trivial thing that one has to do, and we'll discuss best practices of making those sort of decisions. The reason for this is because in most real-world problems, when we're dealing with more than one objective, normally they're in conflict. And what that means is that we'll have to make a trade-off decision. And the question is, what's the best way to do so? The most classical example has to do with when we're trying to balance between price and quality. We constantly do this as professionals when we're creating something, or as well as consumers when we're trying to purchase. We want to minimize the price while maximizing the quality. And this arises in many industries. For example, just think of your food delivery service, right? They have to optimize for three potential stakeholders. They have the people at home doing the orders, you have the restaurants who are providing the food, and then you have the food delivery personnel. They cannot optimize for one group and because they have to consider the other two as well. And that arises in many places. If it's manufacturing, if it's designing of aircrafts, if it's how best usages of land, for example, or chemical engineering. I came across this professionally in the context of drug discovery. And there, for example, when you think about the medicines that we use today, they're made out of small proteins called antibodies. And in order for them to get approved for usage, the engineers have to pass rigorous tests. Here I provide, for example, a shopping list of many characteristics that such a small protein has to pass, and it takes only one for a project to fail. And these projects can be very expensive and also be very long. And so our objective is to identify problems as soon as possible and not have a project fail at a very late and expensive stage. In order to identify multiple parameters and make a decision, we want to apply smart mechanisms. And so that's what we'll be talking about today. We'll talk about the fact that what many analysts do is they actually take multiple parameters and they put them together into a single heuristic, something that's called in the literature single objective optimization. So the advantage of that is it's very simple to do, but there are a lot of shortcomings to that. And so we'll talk about that. And then we'll talk about a solution, something called a Pareto front. And we'll talk about why they are likely to yield better solutions than this common practice of the single objective optimization. Later on, we'll talk about applying this within large intractable spaces. And so we'll talk about a smart search algorithm called a genetic algorithm. Those of you who don't know what genetic algorithms are, that's fine. I'll talk about them from scratch. Those who are familiar with it, the added value is you learn about applying Pareto fronts in the context, because most likely if you do it with multiple objectives, you're actually doing single objective optimization. And so I will address that. And finally, we'll talk about applicability. At this stage, you'll understand, is this relevant for the project you're working on? You'll do so by being able to identify characteristics of when this technique is useful and when it's not. So the way I designed this talk is focused on people who use data to make decisions. And so this could be anybody from an analyst to an economist. It could be if you're a line manager or for your line manager who's interested in having better conversations with analysts to understand the data that's being provided. And you're also interested in improving your optimization skills. There's not much of a requirement, basic understanding of Python, and I don't go into maths at all, so you don't have to worry about that. Just about myself. Hi, my name is Eyal Kazin. I am a data scientist. I started off my career as a physicist. The focus of my research was on observational cosmology. I did research in the context of understanding the Big Bang theory that talks about how the universe expands. And so that was fun. I transitioned to data science in 2014. I currently work in healthcare. Most relevant for this topic today is my work within a biotech company in which I was assigned to optimize for finding DNA sequences to suggest to protein engineers for drug discovery. And so I'll talk about a bit about my experience there in the context of multi-objective optimization. So I'm really psyched about this topic. I think it's a bit overlooked, and I'm really glad that you're interested in learning about it. And so I've prepared a hands-on experience. All the material required for today is provided within the slide. The focus of this video is on this link, in which it really contains all the content and the hands-on material that we'll go through. And later on, I'll talk about these links. So once you press this link, you'll go towards this Google Slides over here. And this is what it looks like. Just skip through towards the agenda part. And this is kind of the construct that we have for today. It's about 2.5 hour section minus what we've done so far. The first part we actually completed. This is the welcome motivation. And now I'm talking about the instructions. Most of this first part, which is fundamentals, we actually have two parts. The first is fundamentals, which I'm talking about right now. Later, we'll have applicability. So right now we're in what I call the live session. Later, after this, you'll work independently using the videos, which now I'll describe. And later on, we'll meet again for the next live session later on. So what I have over here, just focusing on this part, is I provide videos in which I explain the fundamentals of Pareto Fronts, and that's marked here in black. And then here in orange, I mention the hands-on sessions in which you actually will practice this within Jupyter Notebooks. So this first part you can actually skip. This first video is the welcome and motivation. So this is material that we already have done. And so you will want to start from here. And so in each of these slides, what you notice is that there's a play button, and that means that you play and you'll watch the video. You'll learn about the material. I do recommend to do for best quality, just enlarge. So you get the best resolution. So you have this sort of box like right here on the bottom right. And so you get full screen experience, which should be best. So here, for example, I talk about the fundamentals. This is part 1, and here's the timing. So you get an understanding of how much time it will take each video. And here's part 2. So here, again, you'll understand the basics, and then you'll get to practice in Python. And so you can either clone from GitHub, or what I actually recommend you do is just go into Google Collab. What that is, I'm demonstrating here. This is a platform which hosts Jupyter Notebooks, and that you can just go through. Now, these are fully annotated. It has all the material, and you just run through the cells. You can understand everything just going through these Google Notebooks. This Jupyter Notebook, but I do provide also explanations here via video. So you can decide if you want to get those extra tidbits from the videos, but you don't have to. So if you do, you have three videos, 1, 2, and 3. And that's understanding the basic, that's just understanding what a Pareto front is and practicing it. So once you've done that, I do a brief summary video talking about another topic that's called mapping decision to objective space. So I'll talk about the importance of that. And here are a few more slides that we'll talk about later as well. And that's nearly the first part. Just to conclude the first part, to challenge your understanding of what a Pareto front and how to identify it, I created an app. And this app looks like the following. It's called Wacko Pareto Front. And what you'll do is, right now, most of you don't know what a Pareto front is. And so what it is, it's looking within a scatter plot. I'll later explain this in the videos more in detail, but it's identifying an envelope like this, which we call Pareto optimal. And so once you learn that, you'll be challenged to actually apply within a scatter plot. So you look at a scatter plot, and you'll be challenged to see if you can identify a Pareto front. So what you do is you just plug in here how many you think, how many are. I know for a fact that it's 6 in this one. And so I'll just press this button and it will tell me if I'm correct or not. So this happens to be the Pareto front within the scatter plot. And so, yeah, so that's what you'll be doing in this section. And then, so yeah, that's part 1. And then part 2, you'll learn about application of Pareto fronts in the context of a genetic algorithm. So I'll talk about the importance of this and when it might come up in real life. And so here's 2 videos that you'll go through, and then you'll have another hands-on session. And so here you'll have another notebook. This is what the notebook looks like, similar to before. It's fully annotated, it has cells that you just go through with visuals, and that way you can learn the material. Yeah, again, they're fully annotated. You can understand everything you need within it, but I do have 5 videos to help give, again, extra tidbits and information. So 1, 2, 3, 4, and 5. And once you finish that, that's the end of the fundamentals part. All right, so yeah, so far we learned about the fundamentals. Now we'll start learning about applicability. How can we apply this? But actually, just before that, I just want to have a quick summary for your understanding of the fundamentals. So if you remember in the first video, I showed this XKCD comic strip, and we identified the Pareto front when we want to maximize easy and tasty. But let's say we're nasty colleagues of Randall, and we want to give them optimize for difficult and untasty. So what I want you to do is I'll give you about 10 or 15 seconds to think about it. Which are the Pareto optimal fruits that are most difficult and untasty? So think about it. It'll be interesting if you write in the chat how many you came up with without identifying the fruit themselves. Just write in the chat how many you think that are in the Pareto front. All right. Cool. Okay. Nice. So hopefully you got these answers. Okay, it's hard to see by eye, maybe, the grapefruit and lemons, but this is what I came up with, and I'm pretty sure that I got it right. Yeah. So good on you. So that means you are now experts at identifying within scatter plots a Pareto front based on defined objectives. So good on you for that. All right, so we learned about the fundamentals, but now I want to address the question of applicability. When can you actually use this in a project? I mean, obviously there are going to be limitations when you can and cannot. So I started thinking about kind of like a shopping list of what one needs in order to apply. So the first thing I reason is that you want full control over your decision space. And that's not a trivial matter. I first encountered this when I was thinking of food delivery services. I spoke with a data scientist there, and I was sure they were doing multi-objective optimization because they have to optimize for at least three different entities, right? You have the person ordering at home, you have the kitchen, and then you have the delivery person. So that's 3 people that they have to optimize. That's 3 different agents that they have to optimize for. But then I heard from them that they don't use multi-objective optimization. One can argue, well, it is complicated, right? As you've seen, there's a lot of overhead to this process. But another thing that came out of conversation that I realized from them is that they didn't decide which delivery person would pick up in order. That wasn't their decision to make. And so that's why I think that one has to think hard about, first of all, how do you separate your parameters? What's your decision space, meaning what you have control over, and what are you interested in? That's your objective space. So yeah, so they didn't decide which delivery person picked it up. So I consider that decision space. And the next thing is, well, you have a well-defined objective space. And the question is, do you have an inexpensive mapping to go from one to the other? Right? Because right here, what was the mapping? The mapping for us was kind of trivial. It was just doing the sum of the weights in monetary value of packages. But you can imagine, later we'll talk in, you can imagine doing marketing, right? So you have marketing parameters, and then you have the outcome of the marketing. But in order to get these results, if you don't have a model for it, It might have to take days if it's digital marketing, or maybe weeks if it's non-digital. So that will be a constraint. The third question you have to ask yourself is, how big is the expected solution space? Is this something that we can brute force our way quickly? And that means you just open an Excel spreadsheet, for example, and you can just identify and pick and choose. Or is it intractable? And that's most likely most real life scenarios. And so what you'll want is a stochastic mechanism that's smart in its approach in exploring the solution space. And so that's also one example of that is the genetic algorithm that we learned about today. All right, so let's say you have a project, you answer this for this list of demands, and so you can apply multi-objective optimization. So what you don't want to do is go back to my notebooks and copy paste my scripts, because they're really inefficient. So what you will want to do is use like a package like I'm suggesting Deep, which is useful for prototyping. I do want a disclaimer, not a disclaimer, but rather I just want to emphasize that I am not a contributor, I am an end user. So I use this professionally at my work, and I'm a fan of it, so that's why I'm promoting it, but not as a contributor. Yeah, so what I like about it is it has this very nice API that we'll soon use in the next hands-on session. But here I'm just flagging the fact that these functions that we learned in the previous tutorial, here we can, they take care of all the overhead and the maintenance. They take care of all that, and all we have to do is create our individuals and population, and then customize our function. If it's the mate, if it's the mutate, and if it's the evaluate. But most importantly, where you saw that I used a very naive approach to identifying Pareto fronts. And Bill, I remember your question. I'll get back to you later about that. But here you have like access to state-of-the-art Pareto front algorithms. And it's like within this one line of code, you get that power. And so, yeah, so that's what we'll do right now. And so I'm just conscious of time. We have half an hour. So I think I'll go over the notebook for about 2 or 3 minutes. I'll give you like an overview, and then I'll give you some more time so you can actually go through the notebook yourselves. Cool. So this is the notebook. If you're wondering why is there a typo in Deep? Well, that's because it's actually from the acronym of algorithm. And so here within this notebook, I'm basically following their tutorial. So they have a tutorial here called, so they have a tutorial, Knapsack Problem, in which I basically copied from them and annotated a bit and showed, and you notice that I'm very visual, and so I like visual capabilities to their results, to their infrastructure. So so what we're doing over here is, so in this notebook, what you should be doing is, again, we do the same initializing of packages, okay? But then you'll start with the Deep setup. In terms of initiating Deep, you'll have to install it. So don't worry, that's just in this cell over here. Oh, sorry, it's in this cell in which it will pip install in whatever environment you are in. If you're using Collab, then it will work. I tested that. Yeah, so packages as before, but now is the Deep setup. And so here, what you're doing is you have this creator object, and this does all the maintenance for you for creating individuals and calculating and doing all the calculations of, for example, weights over here. So for example, here is how you define your objectives, where this is for single objective optimization. In our case, we'll do multi-objective optimization. So here it's defined by weights, in which we're saying minimize this, maximize that. So this is all detailed within the notebook. And so using Deep, you'll start to create the individuals, meaning the knapsacks, and then the populations of knapsacks. Similar to before, but again, everything under the infrastructure of Deep. And yeah, I'm just going through. Oh, and then another important object is this toolbox. This toolbox is what manages actually the populations themselves. And so go through that. I think it's takes a while to get used to. So if you're not comfortable with it by the end of the session, that's fine. It took me a while to understand what's going on here. But here is where the customized functions. Sorry, let me just move this. So here we're evaluating for fitness. So for example, this is one individual knapsack, and here we have the weight and monetary value. And then we have transformations. And so here I demonstrate how we do the crossover, how we do the mutations, you note that I did a mutation like hack just for visualization purposes. But basically, these functions actually go into this. Remember, I mentioned toolbox, so it has this register. That's where you register all of the custom functions that you're interested in. And then the beautiful thing is, and this is why these packages like Deep are very useful, is they have state-of-the-art selection functions for you. For example, here I mentioned that we imported 2 of them. It's beyond the scope of this tutorial to go into details of why these are useful. I briefly mentioned it in one of the videos, but the main takeaway for today, at least, is this is all it takes in order to use one of these. Just this one line. And that's the nice thing about this. And then here you actually you solve for the knapsack problem, in which I briefly discuss the algorithm. I mentioned the important hyperparameters that go into this, like the number of generations, probability of mating or mutating, things like that. Size of population, how many children. And then you'll actually run it. And then I provide basic algorithms to examine statistics. But of course, I love visualizing. And so you'll have, here you can see how you can visualize. Here's a comparison between the final generation of this run and comparing that to the Pareto front. And then I'm never satisfied with that only final answer. I always like to look into the box like you've seen in my animations, and I like to see the full progress. And so that's why I kind of did a hack over here, and that's what I showed. I just copy pasted their scripts, and then I added my own hack. Like here, I just hacked this part and this, where the motivation is I actually want to trace. I want to actually see the learning. So what I show here is that this is the first generation, second generation, third generation, and then here's the 100th generation, for example. So that's a way, this is how I create my animations, just by tracking the progress. Yeah, so I think that's it. Feel free to ask questions, but for now, just go to slide number, stop this. You'll want to go to slide number 21 and just either use, if you downloaded, use this. If you more comfortable with Collab, just press the button, and I'll try to figure out what time we should reconvene for the last sessions. Any questions? Okay, everybody, let's go back live, and we'll go over a few case studies. So actually, I'm interested in your survey. How many examples do you have in the real life? Energy system, optimization, public policy, emergency triage. Interesting. I'm actually working in this field, and so it's something that I'm kind of like trying to promote internally. Stock portfolio, staffing, carbon, something in science, and primer design of DNA amp. Okay, so the last one is primer design. Okay, so that's actually the last one's most close to what I'm discussing. Again, can everybody hear me? It's hard for me to have any feedback by Zoom.
Yeah.
Okay, cool. So yeah, so I'll talk about 2 case studies in the remaining, what do we have, 12 minutes. Yeah, so my motivation for this was I was working in a biotech lab in which we were using machine learning for drug discovery. In practice, my assignment was I had to work with protein engineers. We had a full-fledged biology labs in which they would order DNA sequences from which we would create antibodies, meaning small proteins. And I had to tell them what we should order so they could design, where the end objective was we had to answer for a few characteristics of antibodies. So here I listed them as something called binding, how one antibody binds with another protein, and potency, which means like how effective it is. I showed you before a shopping list of attributes, but those are the ones that I'm focusing on in this in this study over here. And so this is the data that I was using. And so what it means here is that imagine like this is you're not seeing, this is not DNA, actually this is a protein sequence. So in each position there could be like 20 different, these letters are called amino acids. So those which are just chemical compounds. And that's actually very similar to the knapsack problem. That's why I love the knapsack problem, because it actually happened to be applicable in what I was doing. But here you can see the data is very skewed in terms of, like, in this position here, it's 90% T and only 10% these other squashed letters that represent amino acids. And so I was dealing with a very large combinatorial space, like 10 to the power 26. That's calculated by 20 positions to the power 20 amino acids. So this is my decision space. This is what we order, we can control. Our objective space is the binding and potency. And then we had a machine learning algorithm that if you input a sequence, it will tell you the binding and potency. And so that's the setup. And here I'll just show you, and if you didn't understand that, that's fine. But just to show you, like, to an animation of my decision space. This is a way for me to track what's going on, and it looks kind of hectic, but the way I read it, its frequency changes. I showed you the frequencies before. This is think of this in terms of change of frequency. We hear, for example, it's rejecting this W and it's preferring, instead of that, an A in a W, as opposed to these positions in which it actually likes the initial, what's called the wild type. So that's the decision space. That's how I later create a list in which I tell them what to order. And what we're interested, though, is the objective space. And that's what you can see over here. We started from here, and here you see the Pareto front, like edging on and going closer to the sweet spot. You see it's kind of struggling and it's taking a while. You can see the iterations. But that's the setup that I had. And yeah, I enjoyed this project very much. And so I had a few people interested in machine learning and hyperparameter tuning, and like a lot of things in machine learning is single objective optimization. By now you should be comfortable with this term, and we have the loss function. But in terms of the hyperparameter tuning, I think I have a feeling it would be beneficial to apply multi-objective optimization. One could argue for overhead, but in any case, here I'm just showing a group of data scientists within SAS in which they have a paper in which they applied it to many projects of theirs. And here I'm cherry-picked highlighting one of them called Donors that they worked with their client Donors Choose. And the idea is that they had they were working with this platform, Donors Choose, in which teachers were requesting for project materials, but they were getting a whole lot of proposals in which only just short of 20% of them were relevant. And so they wanted to focus only on, to identify only the ones that were worth their time of reviewing. And so what the data scientists did, they did just a binary classification, and they want to adjust their parameters according to two objectives. And it's minimizing not only the misclassification, but also the false positive rates. Okay, for those familiar with machine learning, for those not familiar with machine learning, I'll just emphasize that a lot of times they do what's called single objective optimization. I apologize if some of this context is going beyond people who aren't familiar with machine learning, but just trying to emphasize that it's an analogy of where we can use this in the technology space in order to solve for problems, for example, in a platform like Donors Choose. That should be a takeaway. In any case, what they're looking at, they're trying to minimize FPR over here, misclassification. And so what they start is they have their vanilla result, just taking vanilla parameter values, and they get this result over here. Then they ask the question, well, can we do better? Well, in these over here, for example, F1, AUC, those that work in machine learning will identify those as single objective optimization, and you can see the results clustering over here. And so what they did is they applied a genetic algorithm, and you can see all the solutions here where they're highlighting in green, they're Pareto optimal, okay? And so from this Pareto optimal, Pareto front, we have to make a decision, right? They have to choose, in their case, only one solution. In my case, for example, when I was doing the antibodies, I actually had to give them a list of about 96. But in their case, they had to choose only one. So one thing they noticed is this bump over here. Okay, and so one aspect that goes into it, and I was asked about this, is constraints. Well, you can decide whatever constraints you're comfortable with. They decide they do not like this bump over here. And so what they did is, and here I'm zooming in, they did a cutoff at this bump. And here's and then they did another, what they called a constrained run, in order to see what they get. And so here you see that in these triangles compared to these circles, they do slightly better. You might argue that's due to stochasticity, but whatever. Whatever works in this case. And so here you can see that they chose this as their best. Again, we talked about subjectivity. This is where subjectivity comes in. So remember that the initial result, the vanilla, was over here. And so one can summarize the results by reducing the FPR by a relative 8%. Okay, and they are improving the misclassification in this direction by an absolute 5%, which is kind of massive in the machine learning world. So I very much like this, and I recommend that anybody who's interested in machine learning and hyperparameter tuning use this. I admit that it is kind of like overhead, and so it's all about, you have to figure out, is it worth your time to do this? So just before the Q&A, I just want to summarize that multi-objective optimization is useful if you're dealing with trade-off objectives, meaning parameters that are in conflict. Instead of using single optimization, in which which does have the benefit of being very efficient and easy to understand, you might be losing out on a big part of the solution space, right? You're putting on horse blinders. So when can you apply multi-objective optimization? Again, you want full control over your decision space. You need an inexpensive mapping from your decision space to your objective space. If you're dealing with an intractable solution space, which is most likely, you want a stochastic algorithm like genetic algorithms. In the slide deck, I provide resources like the package deep and some literature and previous talks that I delivered. And so we have 5 minutes, and so I will be glad to, take questions.